Hello. In this chapter 10, which is the last chapter of this paper differential equation, we will learn about the qualitative behavior of the linear as well as nonlinear differential equations. We will learn about their stability, and we will also learn what kind of figure they generate, that is the phase portrait of both the differential equations. In this chapter, we will discuss the qualitative properties of the solutions of the differential equation of the form x dash, which is equal to dx dt, is equal to f t x, where x is an n cross 1 vector x1 x2 dot dot xn, and f t x is equal to f1 t x1 x2 dot dot xn, f2 t x1 x2 dot dot xn, fn t x1 x2 dot dot xn, which is a nonlinear function of xi's I equal to 1 to n. We will first discuss about various definitions which this differential equation may portray, and at the same time we will start with two differential equations, and then we will generalize to n differential equations. There are several methods available to find a solution of linear system of differential equations, but the same is not true for the nonlinear equations. In fact, there is no method available to solve nonlinear equations. But do we really need an explicit solution at all time? That is, there are many instances where we are not interested in finding a solution, rather we are interested in the qualitative behavior of the solution, which means that what kind of figure the differential equation generates. For example, we consider a population model in which two species compete together for food, shelter, etc. That is, they are competing for space and food. Let x1 t and x2 t be the rates of growth in the population and are connected by a system of differential equation for n equal to 2. Now, for the study of the model, we are not much interested in knowing the exact population of each of the species. Rather, we want to study the respective behavior pattern. In particular, we may think about the following possibilities. Is there any possibility that their competition ends in a draw? That is, the number x1 t is equal to alpha and x2 t is equal to beta forms a set of constant solutions of 1. For such a constant solution, their respective growth rates are stationary, so we call these constant solutions as stationary solutions of equation 1. Other popular names of stationary solution are steady state solution, equilibrium solution, or critical solutions. Throughout this lecture, we will use any one of them in our study. Suppose we have a set of equilibrium solution, that is, both the species are living in an equilibrium state, and we facilitate one species by adding a small number of member of one species, say species 1, and then what going to happen with this perturbed situation? Is there any effect on the equilibrium state or facilitating species 1 will result in winning the competition by species 1 or otherwise? So, what here we will be looking at is not the exact solution of x1 and x2, but what kind of behavior both the species are showing. That is, it may happen that both the species are coexisting, or it may happen that one species dominate over the other and the other species died out. We are going to look into this kind of qualitative behavior in this module. Starting from a set of initial values at a time t equal to t0, what is their asymptotic behavior? That is, what is their behavior for long time, that is, as time t tends to infinite? Is there any possibility that both the species will coexist, or with there any possibility that one of the species dies out. These fundamental queries have a very important role in the study of qualitative behavior of a solution of nonlinear differential equations. The first one is related to the existence of equilibrium solutions, and the second one is about the stability of an equilibrium solution, and the last one is about the asymptotic behavior of the solutions. Finding the answer of the first query is very easy, as the equilibrium state solution x0 t, we put dx dt is equal to 0, and hence we get x1 dash x2 dash dot dot xn dash is equal to 0, and which is only possible if and only if f t0 is equal to 0. We will now explain this whole thing in terms of two equations, which will be very easy to understand, and then we will generalize it to n equations. Consider this system of differential equation, which is dx1 dt is equal to a11 x1 plus a12 x2, and dx2 dt is equal to a21 x1 plus a22 x2, where a11 a22 minus a21 a12 not equal to 0. And if that is the case, if you put this is equal to 0 and this is equal to 0, we will see that there is only one solution, namely 0 0, and hence that is the only critical point of this system. In the second example, which describes the motion of a simple undamped pendulum, dx1 dt equal to x2 and dx2 dt is equal to minus g by L sin x1. And if you put both this equation equal to 0, we will see that there exists an infinite number of critical points, namely n pi comma 0, where n equal to 0, plus minus 1, plus minus 2, etc. Let us now define this critical point for a system of autonomous system given by two equations, dx dt is equal to pxy and dy dt is equal to qxy. If we can find points x0 y0 such that dx dt is equal to 0 and dy dt is equal to 0, that is p x0 y0 is equal to 0 and q x0 y0 is equal to 0, then x0 y0 is called the critical point or equilibrium point. Please note, we calculate this equilibrium point where both the differential equation are constant at this particular time, and hence we put dx dt is equal to 0 and dy dt is equal to 0 and solve the right hand side for this equilibrium point. Our next definition is what is an isolated critical point. So, a critical point x0 y0 of the system 4 is called isolated if there exists a circle x minus x0 whole square plus y minus y0 whole square equal to r square about the point x0 y0, such that x0 y0 is the only critical point of 4 within this circle. And throughout this module, when we mention the critical point or equilibrium point, we will consider them as isolated critical point. Here we will define what we mean when we say that a path is approaching a certain point. What do you mean by an approaching path? Let us consider C to be a path of the system 4, and let x equal to ft and y equal to gt with a solution of 4, which represents C parametrically, and let 0 0 be the critical point or equilibrium point of 4. Then if we say that the path C approaches the critical point 0 0 as t tends to plus infinity, then mathematically it means limit t tends to plus infinity ft is equal to 0 and limit t tends to plus infinity gt is equal to 0. If you look at the figure, you will see that all these paths, they are approaching the point 0 0, but they will not pass through the point 0 0. So, this path will circle about this point 0 0 in a winding manner, but will never enter the point 0 0. So, by approaching, we mean that this will be as close as to the point 0 0, but will never pass through the point 0 0. Now, when we say the entering path, we will mean that in this case the path will actually pass through the critical point 0 0. So, let C be the path of the system 4 which approaches the critical point 0 0 as t tends to plus infinity, and as before let x equal to f t and y equal to g t be the solution of 4 which represents C parametrically. Now, we say that C enters the critical point 0 0 as t tends to plus infinity if limit t tends to plus infinity g t by f t exists, or if the coefficient in 5 becomes either positively or negatively infinite as t tends to plus infinity. So, consider the figure. You will see that all these paths, they are approaching the point 0 0 and ultimately passing through the point, which we say that they are actually entering the point 0 0. So, basically the difference between the approaching path and the entering path is that in approaching path, the path will be in the neighborhood of that point 0 0, whereas in the entering path, the path will actually enters that point 0 0. After defining the entering path and the approaching path, we will now look into the qualitative behavior of the isolated critical points, namely the nodes, the focus, the saddle point and the center. We will now also learn about the stability and the asymptotic stability of the critical point. We now define various characteristic features of the isolated critical point. We start with center. The isolated critical point 0 0 of 4 is called a center if there exists a neighborhood of 0 0 which contains a countably infinite number of closed paths p n equal to 1, 2, 3 dot dot dot, each of which contains 0 0 in its interior and which are such that the diameter of the paths approaches 0 as n tends to infinity. Please note that 0 0 is not approached by any path either as t tends to plus infinity or t tends to minus infinity. Now, if you look in the figure, this contains an infinite number of closed paths which may not be circular in nature, though the figure shows it is a circle, it can be any closed path. So, if we consider this as a circle, you see this consists of concentric circles, each of them contains the point 0 0. And as t becomes large, there will be more concentric circles and this diameter, this tends to 0, and basically the circle will approach the point 0 0. So, basically it is not this circular path that is passing through the point 0 0 or that is approaching the point 0 0. It is this circle which is reducing in diameter and ultimately it coincides with 0 0, and hence as defined that the diameter of the path approaches 0 as t tends to infinity, but 0 0 is not approached by any path, by any of the closed path. In our second example, this is the saddle point. So, the isolated critical point 0 0 of 4 is called a saddle point if there exists a neighborhood of 0 0 in which the following two conditions hold. There exist two paths with approach and enter 0 0 from a pair of opposite directions as t tends to plus infinity, and there exist two paths which approach and enter 0 0 from a different pair of opposite directions as t tends to minus infinity. Now, this statement will be clear if we look into the figure. So, consider these two straight lines, one is this straight line, another is this straight line. So, as you can see that there exist two paths with approaches and enters 0 0 as t tends to plus infinity. So, this is one direction and this is another direction, this point is 0 0. So, both of them are approaching the point 0 0 from opposite directions as t tends to plus infinity. And then consider this particular line, you see this is approaching the point 0 0 as t tends to minus infinity, which means that actually it is moving away from the origin, that is 0 0 as t tends to minus infinity. In the second statement, it says in each of the four domains between any two of the four directions in 4, there are infinitely many paths which are arbitrarily close to 0 0, but which do not approach 0 0 as t tends to plus infinity or t tends to minus infinity. In fact, these paths will be asymptotic. So, these paths are this curved line, and you will draw this curved line in such a manner that please consider this arrow and this arrow. So, it is coming from this and then going in this direction, and hence when you draw this curve, it will be in this direction and the arrow direction will be in this movement. Similarly, if I consider this, then this arrow is going in this direction and then to the right, and this curved path which will be asymptotic to this straight line and this straight line, it will move from this in this particular direction, and the figure which you get is called a saddle. Our next definition is a spiral point or a focal point. So, the isolated critical point 0 0 of 4 is called a spiral point or focal point if there exists a neighborhood of 0 0 such that every path p in this neighborhood has the following properties. Number 1, the point P is defined for all t greater than t 0 or for all t less than t 0 for some number t 0. Second, P approaches 0 0 as t tends to plus infinity or as t tends to minus infinity, and P approaches 0 0 in a spiral like manner, winding about 0 0 an infinite number of times as t tends to plus infinity or as t tends to minus infinity. If you now look into the figure, P can be any point somewhere here or here or here. So, it approaches 0 0 as t tends to plus infinity, which is moving in a spiral manner, and it will not pass through the point 0 0, but it will wind around this point 0 0 in a spiral like manner, and as t tends to plus infinity or as t tends to minus infinity. This figure is about t tends to plus infinity because the arrow is in the direction towards origin. If it moves out of the origin, then it should be t tends to minus infinity. Our next definition is node. The isolated critical point 0 0 of 4 is called a node if there exists a neighborhood of 0 0 such that every path P in this neighborhood has the following properties. P is defined for all t greater than t 0 or for all t less than t 0 for some number t 0, and P approaches 0 0 as t tends to plus infinity or as t tends to minus infinity, and P enters 0 0 as t tends to plus infinity or as t tends to minus infinity. So, if you now look into the figure, P can be anywhere on here or here on this curve, and P first approaches 0 0 as t tends to plus infinity. So, P will be in the neighborhood of 0 0, and the third point says that p will enter 0 0 as t tends to plus infinity, which means that this path will actually pass through the point 0 0 as t tends to plus infinity. And since the arrows are in the direction towards the origin, if this is the case where t tends to plus infinity, and if the arrow is moving away from the origin, that is the case where t tends to minus infinity. We now look into the stability of the system, the asymptotical stability of the system, and when we call that the system is unstable. So, we assume that 0 0 is an isolated critical point or equilibrium point of the system 4, and let C be a path of 4. Let x equal to f t and y equal to g t be a solution of 4 defining C parametrically. We also define dt, which is equal to square root of f t square plus g t square given by equation 6, and this denotes the distance between the critical point 0 0 and the point r, which is f t g t on the curve C. Now, the critical point 0 0 is called stable if for every epsilon positive there exists a number delta positive such that the following is true. That is, every path C for which d t 0 is less than delta for some value t 0 is defined for all t greater or equal to t 0 and is such that dt is less than epsilon for all t greater or equal to t 0. Now, let us look about the visualization of stability, that how the figure looks because of these mathematical expressions. So, in this particular figure, you see two concentric circles k 1 and k 2, one having the diameter delta and the other having the diameter epsilon. 0 0 is the isolated critical point, and this is the point P at the point t 0, and this is the path C, and this is the point R, which is given by the parametric equation f t and g t. Now, we will say that 0 0 is stable if every path C which is inside this circle k 1 of radius delta at time t equal to t 0 will remain inside the circle of radius k 2 for any time t greater or equal to t 0, which means that the path which is generated by this C, they will be contained in this circular patch within the circle k 1 and k 2. It means that at time t equal to t 0, if the path is inside this circle k 1, it will be definitely be inside this circle k 2 if the system is stable. Now, let us look what is asymptotically stable. So, we again assume that 0 0 is an isolated critical point of the system 4, and let C be a path of 4, and let x equal to f t and y equal to g t be a solution of 4 representing C parametrically. And we define the distance dt is equal to square root of f t square plus g t square, which denotes the distance between the critical point 0 0 and the point R, which is f t g t on C. Now, the critical point 0 0 is called asymptotically stable if it is stable and if there exists a number delta 0 such that d t 0 is less than delta 0 for some value t 0, then limit t tends to plus infinity f t is equal to 0 and limit t tends to plus infinity g t is equal to 0. Now, if you look the difference between the stability and asymptotically stability, you will see that asymptotically stable is much stronger than stability, because first it satisfies that the system has to be stable, and then it has to satisfy that it is approaching the point 0 0, because these two are the conditions that the system will approach the critical point 0 0. So, the conclusion is that every path that gets sufficiently close to 0 0 ultimately approaches 0 0 as t tends to plus infinity. So, the basic difference between the stability and asymptotically stable is that if it is asymptotically stable, it has to be stable, and along with that there is a second property which says that if the path gets sufficiently close to 0 0, ultimately has to approach the point 0 0 as t tends to plus infinity. And at the end, a critical point will be called unstable if it is not stable, which means that if it violates any of the property of the stability, then we say that the system is unstable. Summing up, in this module we have learned about the definition of critical points or equilibrium points, various characteristic features, namely the node, the focal point, the center, the saddle point, etc. And we have also learned about the difference between the stability and asymptotically stability. In the next module, we will learn about the phase portrait of the differential equations. Thank you.